Hello everyone, I hope you're doing well. So before starting today's video, I'd like to share with you all that a lot of people who have been watching these videos have not subscribed yet. So if you are one of those who have been enjoying these videos and you find these videos useful, then you can consider subscribing to the channel. It's always free of cost and you can always unsubscribe later. So you can do your part by subscribing and sharing this channel with your friends. So let us quickly start with today's video, and in this video we are going to discuss Geeks for Geeks problem of the day, and today's problem is number of good components, and it is a medium level problem. So this problem says that we have been given an undirected graph with V vertices and E edges, right? And it says a component of the graph is good if and only if the component is fully connected component. So by fully connected means they mean that there is an edge between each and every vertex of that particular graph, right? So this is our question, and they want us to tell how many such fully connected component exists in that particular graph. So this is a pretty straightforward question, and this can be solved with the one simple property of a graph. So according to them, a fully connected graph should look something like this, that all the vertices are connected, right? So we know one property, very important property of a graph, that if there are n vertices or n nodes, then how many edges should be there, we already know it, right? So there are n vertices and each of them should be connected to n minus 1 other vertices, right? So this should be the total number of edges. But since we are given an undirected graph, it means any edge going from a to b is the same as any edge going from b to a, right? So in this formula, we have counted these two edges separately. Now we need to make them one. So what we do is we divide them by 2. Right. So this is the only property you need to know to solve this particular question. Now what you will do is, for example, you have been given some nodes like this. For example, if this is a connected component and this is another connected component and this is some other connected component, right? For each of those connected components, you have to count the number of vertices in that particular component and also calculate the number of edges that should be there. So there will be three different values. The first one is the vertices that you have counted. The second will be the edges that you have counted, and the third will be the edges that should be present for that component to be a good component, right? We have to calculate these three separate values. Now counting the number of vertices is easy, but I think the main trick part here is counting the number of edges. I'll explain you in a while why this is very tricky. So first of all, we have counted the number of vertices. From the number of vertices, we can derive the number of edges that we need for that component to be a good component, and then we can count the number of edges that are actually present in that component, and we can tell whether that component is a good component or not, right? So now let me tell you why counting the number of edges in a graph is a bit tricky. So for example, you might think we can just do simple DFS and we can increment our edge every time, increment the edges counter whenever we visit our new node. So for example, if you are at node this, so if this is something like this, and for example, if this is your DFS function, I'm just writing the pseudo code. So you say if child is not visited, if the child is not visited, then what you do is we increment the edges counter. Why? Because we are going to use that edge to go to the child, and we do DFS on child, right? So this might be something that comes to our mind while we first think of this problem, but this would be wrong. This will give us the wrong answer. Why? So for example, if this is node 1, this is node 2, this is node 3. So while doing DFS, this node is now visited, right? We are initially at this node, so this is visited. Now we go from here to here because this is unvisited. So we mark as this as visited, and we have counted this particular edge now. Now we go from 2 to 3. So this particular node is also visited, and we have counted two edges now, right? The first one is this one and the second one is this one. Now, we have not yet counted this particular edge, and this particular node is also visited. It is already visited, right? So we will never enter our if condition, and our edges counter will never increment, right? So it will only be stuck up to 2. It will never reach 3, which is the actual value. Now, there are some people might think that a solution to this would be placing the edges counter outside the if condition. Now, so this works for now, but we will see how this will this will produce an incorrect answer. So now when we try to go to now when we do DFS, we have one child of this as 1, right? So for example, we have counted this particular edge, but when we go back to 1, then again it has a child 3, then it will again count this particular edge. So there will be duplicacy of edges, right? So again, it will not produce 3 as an answer, it will produce some incorrect values. So like what I did in this solution was, instead of just maintaining a counter, I maintained a set of pairs. So why only a set of pairs? So a set has only unique values. So if I have counted an edge once, it will never be counted again, right? So I will place my set insert function here, where I'm incrementing the edges, but instead of like maintaining a counter, I'm maintaining a set which will automatically maintain the unique values that I have inserted in it. So what are the values that I need to insert in my edge? For example, if I am going from 1 to 2, right? If I am going to 1 to 2, the first thing I can push is 1 comma 2. That there is an edge between 1 comma 2, 1 and 2 that I have pushed, that I have visited. But to avoid duplicacy, right? At the same time, I also push 2 comma 1, right? Because like sometime in the future, we also might try to visit 1 from 2 because they are connected and it is an undirected graph. So at the same time only, I push both of them together, right? At the end, how will I find the total number of edges that are present in my graph? What I do is I just simply do, for example, S is my set, I do S dot size divided by 2. So this will give me my final number of edges, right? So this is the whole problem solution. What you need, I'll just go through it once again, and you will get a clear idea of what we have to do in this particular problem. So they say we have to find the number of good components ever in a given undirected graph. So according to them, a good component is one such component where all of the vertices are connected to each other. Now we know from the property of an undirected graph that if there are n vertices, there should be n into n minus 1 by 2 edges for such a component to be a good component, right? We know we can easily count the number of vertices in a graph. Then we also discussed how we count the actual number of edges that are present in the graph, and we know that these are the number of edges that should be present in the graph for that to be a good component. So we know the actual value, we know the needed value, what we need, and we can just check whether they are equal or not. If they are equal, then we can obviously take that component as a good component, otherwise we cannot take it. So counting the number of vertices is easy, but counting the number of edges is not that easy. So what we'll do is we'll maintain a set of pairs in which we will insert, whenever we are going from 1 to 2, we are going to insert 1 comma 2 and we are going to insert 2 comma 1. So if we are going from node to child, we are going to insert node comma child in the graph, in the set, as well as we are also going to insert child comma node in our set, right? At the end, how do we get the total number of edges in our graph in any connected component? We just do our set dot size divided by 2. So this will give us the number of edges in our connected component, and we know the actual number of edges that are present in a connected component. We know what are the number of edges that we need. We can just equate them and check whether they are equal or not. If they are equal, then we have one more good component in our given input. Otherwise, we do not count it as a good component. So this was the whole explanation. Now let me just show you the code of this particular problem. So this here, if you can see, this is the main function that we are given, and I initialize my answer with 0. I initialize my visited vector with all values false, right? Here I also initialize two global variables. the first one is an integer vertices, which will count the number of vertices in any connected component. And as discussed, I have also initialized a set of pair of called edges, right? Now I just go from each of the vertices. I just go on each of the vertices from 1 to less than v plus 1. So it is from 1 to v, and if the current vertex is not visited, that means I have found a new connected component. So what I do is I initialize my vertices counter with 0. I clear my edges set. Now I just do simple DFS stuff. So the current node will be I pass the visited vector and I pass the adjacency list. As soon as I get into the DFS, what I just do is I just increment the counter of vertices. I mark my current node as visited. So I just visit every child of the current node in the adjacency list. So that is why what is happening in this loop. That is what is happening in this loop. And for each of those child, I just insert in the edges set a pair node comma child and another pair child comma node. Right. So these are the two pairs I'm inserting into the edges set. Now, if the current child is not visited, I'll just call DFS on that particular child, and this is all about the DFS function. Now, when I return from this DFS function, what I just do is I try to calculate the number of edges that I actually need for the current component to be a good component. So it should be equals to vertices into vertices minus 1. So this is what is happening here. This is just the shorthand notation. So this step is actually if n is the number of vertices, n into n minus 1. So this is what is happening in this particular step, and in the next step I'm just doing vertices right shift 1. So this is actually n by 2, right? So this is the whole process of computing the number of edges that I need to like for the current component to be a good component. Now I just add some value to my answer, and that value is a boolean value. So it will be true or it will return 1 whenever vertices is equal to edges.size divided by 2. So I have already explained you that edges.size divided by 2 will give me the number of edges that are actually present in my current connected component, and vertices now, and the vertices variable now has the number of edges that I actually need for the current component to be a good component. Right. So I just equate both of them. If they both are equal, it will be true and it will return 1. Otherwise, it will return 0. Right. So the corresponding value will be added to my answer. At the end, I just return my answer, and this will be the solution for today's problem of the day, number of good components. So I hope you guys were able to understand the solution. If you guys did, then you can show your appreciation by clicking on the like button, and don't forget to share this channel with your friends. So till the next video drop, stay safe, keep coding. Bye bye.